Okay, so here's a couple of examples to the Bell activity. So here's two numbers with the same exponent, 2 squared, 3 squared. And then when we multiply those together, we have open paren 2 times 3, close paren, squared. Okay, so that would turn out to be 6 squared, which in the end would be 36. Okay, so when you multiply powers, if they're the same, you keep that power and you multiply the base. Okay, so you keep the power. If the powers are the same, you keep the power and multiply the base. Down here, here's another one. 4 cubed times 5 cubed. Their powers are the same, so you keep the power here and multiply the bases. 4 times 5. So this would become 20 to the third power, which would be 20 times 20 times 20. And for the same index, here's a couple of examples using two numbers. We have the square root of 2 times the square root of 3. Well, our indexes are the same. Because our indexes are the same, we can combine those into one index of 2, or radical 2 times 3, which would be radical 6. And here we have the cubed root of 4 times the cubed root of 5. So because these indexes are the same, because the index is the same, we can just keep the index and then as the radicand multiply the initial radicands, 4 times 5. So this becomes the cubed root of 4 times 5, or the cubed root of 20. So this brings us to a property about combining radical expressions with products. It says if the nth root of A and the nth root of B are real numbers, then the nth root of A times the nth root of B equals the nth root of A times B. So let's put this to use. Our first problem, multiplying radical expressions, asks us, can you simplify the product of the radical expressions and explain? So the first problem says cubed root of 6 times square root of 2. Well, you need to look at the index. We've got a 3, and this one would be a 2 because it's square. If there's no index there, it's assumed to be 2. So 3 and 2. They're not the same index, so you cannot multiply those together. So the answer, no, the indexes are different. The property above does not apply. The property on the previous page does not apply because the indexes are different. B, so we have cubed root of negative 4 times the cubed root of 2. So our indexes are the same. So we can do the multiplication property on the radicands. So this would become radical 3 and negative 4 times 2, which would become the cubed root of negative 8. And we know that that's going to be equal to negative 2. And we don't use absolute value symbols because this was an odd index. Okay. Okay, our godets are here. If you'd like more practice at this point, pause the video, work these out, and then we'll continue. Okay, so moving on. If the radicand of the nth root of A has a perfect nth power among its factors, you can reduce the radical. If you reduce a radical as much as possible, the radical will be in its simplest form. For example, consider radical 24 and the cubed root of 24. So let's look at the first one. Square root of 24 is equal to, so the first thing we want to do is write this in terms of something that we can square in the factors. So we know 4 is a perfect square, and it's a factor of 24, so we'll use it. So our index is 2, so we want to try to make things power of 2 so we can clear them. So we have 4 times 6, and we can rewrite 4 as 2 squared times 6. And now that would be equal to square root of 2 squared times the square root of 6, which is equal to square root of 2 squared is 2, and we're going to leave the square root of 6. So 2 square root of 6 is in its simplest form. Okay. Next, look at the cubed root of 24. So the first thing we're going to do, we need to write things in cubes so we can clear them. So the first thing, we know that 8 is a perfect cube of 2, so it's going to be 8, which is a factor of 24, so we'll use it. 8 times 3, which is equal to the cube root of 2 cubed times 3, and then split them up. The cube root of 2 cubed times 3, cubed root of 3, and we can clear that out. Simplify the cubed root of 2 cubed is 2, and leave the 3 cubed root of 3, and that's our answer.